Hi, welcome back. We're in lecture 10, and the topic of the lecture today is confidence intervals. In the first segment, I introduced the idea of confidence intervals in the context of sample means. In this section, we'll look at confidence intervals around regression coefficients. So again, a confidence interval can be applied to any sample statistic. So this segment is actually very repetitive of the last segment. A lot of the concepts are the same. I'm just going to apply those concepts to a regression coefficient rather than a sample mean. For some reason, in actual reporting of statistics, as I said in the last segment, a lot of researchers are sort of uneasy about reporting confidence intervals, partly because they're so large. But worse than that is they're rarely applied to things like correlation or regression coefficients. For some reason, people understand that there's variability around a mean, but they're less prone to apply that same logic to a correlation or a regression coefficient. But remember, a correlation coefficient or regression coefficient, they too are sample statistics. So they too are just point estimates. And it would be better if we were reporting interval estimates. So again, this all is the same as what I said for a sample mean. We have a regression coefficient. If that's just from one sample, it's a point estimate. What that means is it represents just one point in this possible sampling distribution. So remember, from regression, we can get a t-value, and R gives you that because it gives you a t-value and then a p-value associated with it. And the t-value was just the unstandardized regression coefficient, b, over the standard error. And again, that's just going to fall somewhere in a sampling distribution. So again, it's just going to be some point in a sampling distribution. If it was there, we would say it's not significant, right? Because it's not very extreme. But if it was like way out here or way out here, then the probability of landing there is very low. Under the assumption that the mean is 0, then we would reject the null. Again, this is the same as I said in the last segment. The logic here is to report a range of values rather than a single value, report an interval estimate rather than a point estimate. And again, the argument for this is the reality of sampling error. If we know that we have a large population and we're only getting a very small, even if it's representative, if we're getting a small sample, then we have some degree of sampling error, and we have to acknowledge that. And one way to acknowledge that is, rather than report a point estimate, just report the interval estimate that takes into account standard error. Again, this is the main point from the last segment, and it's the take-home message from the entire lecture. The confidence intervals are going to be influenced by, the width of them will be influenced by standard error, which is influenced by sample size and variance in the population. So again, let's go to back to this impact example. What I'm going to do is run a regression predicting visual memory score from verbal memory score. And I use these two variables because they showed a really nice degree of correlation, if you remember, in our overall sample. I think the correlation was in the range of like 0.4 something. So we should get a nice prediction and a significant regression coefficient if we were doing null hypothesis significance testing. But what we can do is get an interval around that. And again, just like I did in the last segment, we'll do it for two different sample sizes so we see how the interval gets wider as we decrease the sample size. So we'll start with a sample size of 40, and here's what the regression looks like. So I'm just plotting the scatter plot with the regression line. So that's the actual slope that I got. That's the point estimate, is the blue line. That's the slope relating verbal memory to visual memory. So that's B in the regression coefficient. But that's just one number. That's a point estimate. If I want to get the confidence interval, Well, I got that out of R, and then what I did is I just plugged it into the scatter plot, and that's what you see in the shadow around the regression coefficient. So what this shows me is the possible range of regression lines that I could expect due to chance. So how this works is I could get one, let me erase that. So the regression line could be as steep as, if I start at the very bottom of this shaded area, it could be as steep as this. So that's the upper bound of the confidence interval. So that slope would be the upper bound in our confidence interval. Or it could be as shallow, if I start from here and go to here, it could be as shallow as that. Notice that that's still a positive slope. So in this shaded region, I don't have a flat line, and I don't have any negative slopes. So you can interpret from this visual, this graphic, with this regression line and this 95% confidence interval around it, you could interpret this to be a significant relationship between verbal memory and visual memory. Again, hardcore statisticians would argue you're reporting confidence intervals to get away from the idea of statistical significance and NHST. But those of us who are so prone, and it's such a habit to think, is it significant or not, would look at this and see, well, I can't get a flat regression line in there in this shadowed region. That means it's a significant effect. So that's sort of an argument against confidence intervals, is when you report them like this and you report a visual, even if you report the interval, and if 0 is not in the interval, then you can assume, or you can infer, excuse me, you can infer that it's statistically significant. So even with confidence intervals, you can still sort of run into this problem of the idea of significance. But let's look at the interval and the width of this shaded region as we decrease sample size. So now again, I use the impact data, but now I just got a random sample of 20, same exact variables, same exact regression, so it's still LM, visual memory, tilde, verbal memory. And now look what it looks like. We have a regression line that's similar to the last example because that's my point estimate, but the shaded region around it is much larger because the standard error went up. Why did the standard error go up? Because n went down. So now you see that I can put a flat line in there. I could just go. So it's possible that the true population parameter for B is 0. If that's possible, then you would get a non-significant p-value if you were doing NHST. But the bigger point here is to show how wide that interval is in the scatter plot when sample size went down. The other point to take away is you really should be doing this anytime you report a scatter plot, correlation, or a regression. If you're showing a scatter plot, it's really nice to put that confidence interval, or at least the standard error, around it, again, to indicate and to acknowledge that you have just a point estimate. You have just one sample, and you have some degree of sampling error. How much sampling error? Well, that's reflected in the width of the shaded region, which is driven, again, by standard error. So it's really nice to put those in there. We'll do that in the lab, and we'll give you a script that shows you how to generate a scatter plot with this shaded region reflecting standard error or confidence interval. So again, to wrap up this segment, it's the same summary as the first segment. It's this very important point that all sample statistics, not just means, but correlation coefficients, regression coefficients, anything else you take away from one sample, they're just point estimates. And that means they just reflect one point on this idea of a sampling distribution. So the logic of confidence intervals is to report a range of values rather than just a point. So we report an interval estimate, not a point estimate. And finally, the width of the confidence interval is just going to depend on standard error. And standard error depends on sample size and variance in the population.